Imagine a gas capable of changing the course of history. It can disinfect water, create plastic without which modern life is unthinkable, and at the same time become a deadly weapon. This is chlorine. Annually in the United States, over 12 million tons are produced, as much as 120 Gerald Ford aircraft carriers weigh. But the real mystery isn't in the numbers. It's hidden in the technology itself. How does simple salt water, with the help of electricity, give birth to three products that support entire industries? Watch carefully. At the end of this video, you'll learn a fact that will forever change your understanding of this invisible foundation of modern civilization. The United States is one of the world's largest producers of chlorine. Annually, factories in the country produce over 12 million tons of this gas. This figure simply doesn't fit in one's head. Imagine the weight of the Gerald Ford aircraft carrier, the world's heaviest military vessel. That's about 100,000 tons. This means that in 1 year, American industry produces as much chlorine as 120 such carriers weigh. Everything begins not in a laboratory, but deep underground. The main ingredient for our recipe is ordinary rock salt, or sodium chloride. It's either mined in mines or, much more efficiently, pumped from underground. Water is pumped into deep underground salt deposits. The water dissolves the salt, forming a saturated saline solution called brine. And it's precisely this concentrated salty solution that's our raw material. But it's still dirty. It's full of impurities, calcium, magnesium, and other minerals. Therefore, before the main show begins, the brine undergoes thorough purification. It's passed through an entire series of tanks where, with the help of chemicals, all impurities are precipitated and filtered from it. At the output, we obtain a perfectly clean, transparent, and very salty solution, ready for the main event, electrolysis. These are electrolyzers, or cells. It's precisely here that all the magic will occur, or more accurately, all the chemistry. Let's imagine one such electrolyzer. Essentially, it's a box into which our pure saline solution is poured. And into this solution are immersed two electrodes, a positively charged anode and a negatively charged cathode. Now to these electrodes is applied a direct electrical current of colossal force. And here the breakdown begins. The salt molecule in water breaks down into positively charged sodium ions and negatively charged chlorine ions, and the electrical field forces them to move. The positive sodium ions, like a magnet, are attracted to the negative cathode, and the negative chlorine ions to the positive anode. Two such chlorine atoms, having lost their charge, immediately unite, forming a molecule of gaseous chlorine. Billions of these molecules gather together and on the anode surface begin to appear tiny bubbles of greenish-yellow gas. This is our chlorine. The main resource for chlorine production is electrical energy. The chlor-alkali industry is one of the largest consumers of electrical energy in the United States. To produce 1 ton of chlorine requires approximately 2,500 kilowatt-hours of electricity. Now, let's multiply this by 12 million tons per year. It turns out that this industry annually consumes about 30 billion kilowatt-hours. That's more than the annual electricity consumption of entire states such as Vermont or Wyoming. but they don't transform into metallic sodium. Instead, electrical current splits the water molecules present in the solution into hydrogen and hydroxide ions. At the cathode are released bubbles of pure hydrogen. This is our first byproduct. And the hydroxide ions remaining in the solution combine with our sodium ions, forming sodium hydroxide, or caustic soda. This is our second incredibly valuable byproduct. But here arises an enormous problem. We've just obtained three substances: chlorine, hydrogen, and caustic soda. And they must not be mixed under any circumstances. Chlorine and hydrogen together form an explosive mixture. And chlorine and caustic soda react, forming bleach, which we don't need at all. This membrane, made from special polymer, resembles a bouncer at a nightclub. It allows positive sodium ions through, permitting them to pass to the cathode, but blocks negative chlorine ions, preventing them from entering the cathode space. Thus, chlorine is born and collects in one part of the cell, whilst hydrogen and caustic soda collect in another. Now we need to gather our harvest. From the anode chamber is continuously pumped wet, hot, greenish-yellow gas. First it must be cooled. Then it must be dried. Chlorine is incredibly aggressive, especially in a wet state. It corrodes almost everything. But there's one substance it doesn't touch: concentrated sulfuric acid. It's compressed under enormous pressure and simultaneously cooled. Under this double assault, the gas transforms into a transparent, amber-yellow liquid resembling oil. This liquid chlorine is far more convenient to transport and store. It's poured into special thick-walled steel tanks or railway wagons. Every step of this process occurs under conditions of absolute seal, because leakage of this gas is deadly dangerous. And what about our byproducts? They're no less important. The hydrogen we obtained is collected, purified, and used either as fuel for the factory itself or sold. And the caustic soda solution that formed is pumped out, concentrated, and sold. And so, from simple salt water, passing through it an enormous quantity of electricity, people have learned to obtain three extremely important substances at once, which are the foundation for thousands of other products. Now let's look at where all this enormous quantity of chlorine goes. You might think it all goes to disinfecting swimming pools, but that's merely a drop in the ocean. In reality, less than 5% of all chlorine is used for water disinfection. And where does the remaining 95% go? It's a key building block for other products. About 40% of all chlorine goes to producing this universal plastic. Vinyl windows in your house, water pipes, medical drips, the credit card in your wallet, all of this was born thanks to chlorine. Another 40% approximately is used for creating thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides, the list is endless. And chlorine is also a key component for bleaching paper, giving it that very clean white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we obtain approximately 1,100 kilograms of caustic soda. This means that annually, American industry produces over 13 million tons of this important alkali. This makes chlor-alkali production a perfectly balanced business. Imagine a substance that doesn't melt, leaves not a single drop of water, and simply vanishes into thin air. It can freeze anything within seconds, create thick white fog that rolls across the ground, and even stop life itself if handled carelessly. Dry ice isn't just cold, it's a controlled force of nature that humans have learned to harness. Deep beneath the hum of compressors and swirling clouds of white vapor lies a process that seems like magic, where gas transforms into solid matter at -78 degrees. But where does this gas come from on an industrial scale? And why is dry ice production considered a genuine environmental miracle? Watch until the end and you'll see how something so cold can become one of the hottest businesses in the world. Industrial dry ice is nothing other than solid carbon dioxide, which freezes at the extreme temperature of -78.5 degrees Celsius. Put simply, it's the very same carbon dioxide we exhale with every breath, which plants absorb and which gives fizz to your favorite carbonated drinks. Unlike ordinary ice, which melts into water, dry ice possesses a remarkable property: sublimation. It transitions from solid state directly to gas, bypassing the liquid phase entirely. That's why it's dry. It leaves no puddles behind, simply disappearing into invisible gas. This unique ability to cool instantly and evaporate without trace has made it indispensable across dozens of industries. In medicine, dry ice is a genuine guardian of life. It's used for transporting vaccines, donor organs, and blood, where every second's delay and every extra degree could cost a life. In cryotherapy, it's applied for targeted freezing and removal of warts. In the food industry, it's become a guarantor of freshness. Frozen products, meat, and ice cream are transported in containers filled with this cold wonder. And in the world of entertainment, dry ice is the chief instrument for creating magic. The thick, heavy fog rolling across stages at concerts and theatrical performances, or smoking cocktails in bars, all of this is the work of dry ice, which creates impressive visual effects when it contacts hot water. Dry ice production takes place at cryogenic plants. These facilities occupy enormous industrial areas, comparable to several football pitches. At the center of the site stand gigantic cryogenic tanks, steel towers up to 50 feet high, capable of holding up to 100 tons of liquid carbon dioxide. Inside the workshops, there's a constant hum, powerful compressors and hydraulic presses at work. From the giant tanks, liquefied gas flows through thick, frost-covered pipes into the very heart of production, the pressing installations. These machines are absolute monsters, capable of compressing up to 500 kilograms of dry ice in a single minute. When liquid carbon dioxide under enormous pressure bursts from the nozzle into a chamber at normal atmospheric pressure, rapid expansion occurs. This process, known as the Joule-Thomson effect, causes the gas to cool and freeze instantly, transforming into loose, snow-like dry ice. A cloud of thick white vapor rises above the pressing chambers as powerful hydraulic presses, with force measuring hundreds of tons, compress this snow into dense, heavy briquettes or fine pellets. Conveyor belts move continuously, carrying away the icy blocks. They pass through refrigerated tunnels where temperature is kept below -40 degrees. Automated machines slice large slabs into smaller pieces or transform them into pellets the size of peas. Packaging machines work at lightning speed. Precisely calculated quantities of dry ice are poured into special polystyrene thermal containers, from small 1-kilogram packets to enormous containers holding hundreds of kilograms. Automatic sealers hermetically close the packages to slow the sublimation process. In 1 hour, a single such plant can produce about 5 tons of product. Now imagine the working conditions in this frozen kingdom. In zones where presses and packaging lines operate, temperature stays below -40 degrees. Workers here resemble polar explorers. They're dressed in multi-layered thermal insulation suits, wearing special gloves on their hands, since direct contact with dry ice causes instant and extremely painful burns. On their faces are protective goggles and masks, as high concentrations of carbon dioxide in the air can cause dizziness and suffocation. Because of this, powerful ventilation systems must operate in the premises, constantly refreshing the air and maintaining safe oxygen levels. To avoid hypothermia, workers labor in short shifts, alternating work in cold zones with breaks in warm restrooms. Many processes are maximally automated to reduce human presence in extreme conditions. But even with such protection, work at these plants demands incredible endurance and the strictest adherence to safety procedures. So where do plants obtain carbon dioxide in such colossal quantities? The secret is that they don't produce it specially, they collect it. It's a byproduct of other major industrial processes. The main sources are ammonia and fertilizer plants, breweries where gas forms during fermentation, as well as petroleum refining and cement works. Rather than releasing this carbon dioxide into the atmosphere, it's captured by special installations. The gas then undergoes multi-stage purification from impurities, is dried and compressed under high pressure, transitioning to liquid state. This process is the brightest example of industrial symbiosis and circular economy, where waste from one production becomes valuable raw material for another. But for all its usefulness, dry ice is a substance requiring extreme caution. Its temperature is so low that it can cause serious burns upon contact with skin. But the main danger lies in its sublimation. Whilst evaporating, dry ice displaces oxygen from enclosed spaces. Being in an unventilated room where large quantities of dry ice are evaporating can lead to suffocation. Tragic cases are known where people suffered fatal poisoning using dry ice to create fog and enclosed swimming pools. Therefore, working with it requires strict adherence to safety rules, good ventilation, use of protective gloves and goggles. Now let's glimpse into the future, because dry ice has an incredibly exciting one ahead. Right now, scientists and engineers are developing technologies where dry ice plays a key role. For example, in fire suppression. Unlike water or foam, dry ice doesn't conduct electricity and leaves no traces, making it ideal for extinguishing fires in server rooms, museums, or power stations. Dry ice pellets are sprayed onto fire, instantly cooling it and displacing oxygen. Another direction is cryogenic cleaning or blasting. Tiny dry ice pellets are fired under high pressure at contaminated surfaces. Striking them, they instantly evaporate, and the micro-explosion caused by rapid gas expansion literally blasts off dirt, paint, or rust without damaging the surface itself. But the most fantastic prospect is terraforming planets. Scientists are seriously considering the possibility of using carbon dioxide, which in solid form covers Mars's polar caps, to create an atmosphere. By melting Martian dry ice using nuclear explosions or gigantic mirrors, one could trigger a greenhouse effect that would warm the planet and make it habitable. So this cold, smoking material that we use today for cooling drinks might one day become the key to transforming the red planet into our second home. This proves that even the most ordinary-seeming substances conceal within them boundless potential that humanity has yet to unlock.